Okay, so welcome back to class. So this is week 6 and on polymers. And this is basically lecture number 11 and 12. So this will have 3 or 4 half an hour slots. And the topic of discussion will be blobs in polymers. And I want to tell you that there are various kinds of blobs which you see in literature and in the papers, and it is typically used to figure out the spread of a polymer chain under various conditions, and also the how much would be the energy of interaction and so on. But we'll discuss that. And what I want to tell you is basically that. Uh, there are various kinds of blobs, tension blobs, compression blobs. You hear about Pinkus blobs, various blobs due to confinement. And what I've done in this course or in this, the way we're presenting is uh, collect all the concepts of blobs and discuss them one after the other uh, in this week, in this set of 2 or 3 lectures, half an hour lectures. Though actually in the books, basically these ideas, the idea of the various kinds of blobs is developed in different parts of the book while discussing different topics. But I thought if I put them all together, it will help so that when you hear about blobs, adsorption blobs, thermal blobs, tension blobs, which by the way is the same as Pinkus blobs. So in some places you hear the word Pinkus blobs is used. It's the same idea as the tension blobs. Then there are compression blobs, which are basically blobs due to confinement effect. You can have various kinds of confinement. The confinement in a cylinder. Now, suppose you are looking at DNA organization at long length scales, and you look at DNA at suppose 15 nanometers or 100 nanometers length scale, and you want to ask how is the DNA polymer organized within a bacterial cell, which by the way has no nucleus. Then again, you can use the idea of blobs if you're using looking at DNA from the polymer physics perspective. You can also look at uh, polymer, the arrangement or the extent of polymers and the idea of blobs when a polymer is confined within 2 parallel plates. One can also have the correlation blob, and that is typically comes up during discussions of semi-dilute polymer solutions, and that is in page 177 of Rubinstein. You can have also blobs in polymer brushes, but we are not going to discuss that. So what is a blob? It's essentially a measure of the extent of a polymer or a segment of a polymer. Why do we care? What are the kinds of questions that will be discussed? I mean, what are the physics questions? So blob is a theoretical concept which helps us calculate. But what are the kinds of physics questions will this discussion of blobs help us with? The broad question will be, now if you have a single chain, dilute polymer chain, right? On one limit, you have the athermal solvent, athermal polymer, athermal limit of a polymer, where basically a monomer does not distinguish between, in terms of interaction, doesn't distinguish between a monomer-monomer interaction, the monomer-solvent interaction. The strength is the same. If you have forgotten, please refer to my lecture 6, week 3. But if a polymer is very dilute and extended, and the monomers don't even interact with much itself, right? Then one can actually use the ideal chain approximation, where the RG, the radius of gyration, or the end-to-end vector, goes as n to the power half. Whereas, as you know, when excluded volume interactions become important, when the polymer is a athermal, then the extent of the polymer as measured by the radius of gyration or the end-to-end vector goes as n to the power 3 by 5, which is the so-called Fourier exponent. So to decide when a chain will swell, so that you have to use this description, or you can live with this description. One has a parameter which is called the chain interaction parameter, and which goes as V. What is V? It's the excluded volume parameter as different from the excluded volume. So excluded volume parameter is basically this V quantity integral over all space 1 minus e to the power minus interaction potential by kBt into d3r. Right? This is the excluded volume parameter V, which again was discussed in lecture 6, week 3. So if you have forgotten, please look it up. That's different from the excluded volume, because excluded volume will be the diameter, right, of the monomer. So the two monomers cannot overlap. But even if they can't overlap and there's some excluded volume, right, basically there could be also attraction between the monomers. And so this excluded volume parameter V takes into account both this solid diameter of the monomer as well as the interaction, if there is an attractive interaction. And so basically, just to remind you, when this excluded volume parameter is equal to 0, this does not mean that excluded volume is equal to 0. So monomers cannot still sit on top of each other. But when this parameter becomes 0, then the polymer behaves like an ideal chain, and that's what you call the theta solvent, right? On the other hand, if B is equal to B square D, what is B? Suppose this is a polymer chain, and the distance and the bond distance between adjacent monomers is suppose B. Taking it as a Kratky-Porot model, as like rods, polymer is more like a rod-like, basically like a rod between two monomers. I mean, between the bending, and basically the width of these cylindrical objects is D, right? And then actually the area of the cylinder will go as pi d square B, but the excluded volume parameter V goes as B square D. And when V is equal to B square D, you call it the athermal polymer in a athermal solvent conditions, where monomer interaction is equivalent to the monomer solvent interaction, and then Rg, the dimension, the spread of the polymer always goes as n to the power 3 by 5, just to remind you. And when B is less, when V is less than B square D, then you say it's a good solvent. And then V becomes smaller, the attraction increases between monomers increases. At one stage, V can become equal to 0, and that's when the entire polymer chain behaves like an ideal chain. And the ideal chain approximation is valid. Rg goes as n to the power half, and then V is negative, then the chain collapses. So collapses means it is in a poor solvent or bad solvent. Okay, so with this background, basically to answer such questions as these, we introduced the idea of blobs, and this discussion is essentially from page 113, Rubinstein section 3.3.1, and it's essentially a length scale within the polymer. So what I have done is draw various polymers, and what I want you to see is basically the polymer in the, the central part of this black polymer is basically surrounded by other monomers from the same polymer, and only if you go larger than a certain length scale does this polymer gets to meet the red polymer or the blue polymer or the green polymer. And that is true for the blue one also. For a large region, for a large length scale, all these monomers are the monomers of the blue polymer are seen if at all it is coming in contact with other monomers, it is seeing monomers of the same blue polymer. But if it go above a certain length scale zeta, okay, then it gets to meet monomers from other polymers, say this green one and the black one, and so on and so forth. So the message is, so zeta is a length scale above which it's a length scale which defines a blob, and it's only above this length scale that the monomer of one blob is defined by a length scale, a collection of monomers, or a length of the segment, segment of the entire polymer chain, part of the polymer chain, which of course has its own different conformations. And this segment of the polymer chain in its various conformations, I mean random walk conformations, say, right, only if these monomers interact with an interaction energy equal to kBt with another blob. So monomers at times are touching each other and at times are not touching each other, right? On an average, the number of contacts might be less, but as you increase the segment of the chain, there is more probability of contact between monomers, and zeta is that length scale, is that, I mean, along the contour, it would have gone, I mean, it would have rearranged in itself at the length scale where the average interaction between these monomers, which constitute a blob, have an average interaction of kBt with another set of monomers which constitute a neighboring blob, right? So that's the idea. So at length scales greater than zeta, interaction between blobs matter, and that's the order of kBt. At length scales less than zeta, basically you have unperturbed conformation statistics. And depending upon what the physics is, it could be swollen or ideal below the length scale of blobs. So above the length scale of blobs, above length scale zeta, blobs interact with each other with energy kBt. Below that, it's relatively unperturbed. There's not much interaction. At the length scale less than zeta, there's not much interaction. This is the key idea which you will see will keep getting repeated as we discuss different kind of blobs, say thermal blobs and compression blobs, and so on and so forth. So there will always be a length scale, and above that length scale, there will be interaction of kBt between blobs. Okay, so with that, this is the general idea of blobs. It will always be defining a length scale, a segment of the polymer chain. But now we shall discuss the particular case of thermal blobs. And this is from this section of Rubinstein, which you can refer, of course. So what is the idea? So it's at a length scale L, okay? With the length scale L, if it is smaller than zeta T, the T stands for thermal blob. To remind you that the zeta T is for the, we are talking of the thermal blob. So excluded volume interactions at length scales less than zeta T is less than kBt. So you can assume an ideal conformation. Okay. So zeta T is the thermal blob length scale. And basically at that length scale, the thermal blob would contain, suppose GT monomers. T again stands denotes thermal blob. G is the number of monomers which constitute of a part, a segment of the entire polymer chain, right? And B, as we discussed in the previous slide, is the bond length or the bond diameter. And then zeta T will be equal to B into G to the power half. because below that length scale, there's not much interaction between the monomers. Okay, I mean, the interaction is less than kBt. So you can take an ideal chain conformation at length scales below zeta t, and for GT monomers, and hence zeta t is Pg to the power half, and the total number of blobs in the entire polymer chain will be n. N is the total number of monomers in the chain divided by GT, right? Because GT is one blob. How many blobs there are in the entire chain? N by GT. And after this, we are going to take a Flory kind of argument where we're going to calculate free energy of interaction for a monomer, per monomer. Okay. And suppose two monomers come in contact with each other, the average energy of interaction will be kBt, right? Because that's all that they can have. I mean, it has an average thermal kBt kinetic energy. They're going to move towards each other. I mean, that's the approximate amount of energy that they can overcome in potential, right? So the energy of interaction would be kBt, and per monomer, what is the probability that it will interact with some other monomer? That's equal to the density of contacts, right? So if the contact density is very low, where it's very low probability of two monomers coming in contact with each other, then the mean energy will be less than kBt, right? So basically what we are saying that, okay, then the mean energy of interaction is the excluded volume parameter V into I mean, which is the basically the volume of a single monomer, effective interaction volume of a single monomer. That's why V, kBt into V into density of contacts, and density of contacts is basically GT. It will depend upon the density of monomers. It is not equal to, but will depend on the density of monomers, and that is equal to GT is the number of monomers in volume zeta t whole cube. Of course, we are not putting in 4 pi by 3, right? Because it's an estimate. It's an order of magnitude. That's what we are calculating. And if there are GT monomers in this volume, so for each monomer, this is the problem. I mean, this is proportional to the probability of contact, and energy is kBt into that. And for GT monomers, this is for one monomer, and for GT monomers, it is GT into this quantity, right? So kBt into density of contacts into this, and so on and so forth. So now the question we are asking is over what length scale? Okay, so what I've written is the same thing: free energy of interaction for GT monomers in volume zeta t whole cube is equal to kBt into V into GT whole square, GT into GT upon zeta t whole cube. And now we are asking at what length scale will the interaction energy, this interaction energy, so at what length scale zeta t, that's an unknown thing. That's what we have to solve for. We don't know what is the size of a blob, but we know that as you go on increasing zeta t, there will be more and more monomer contacts. The probability of contacts is going to increase. There will be more monomer contacts, and at a certain length scale zeta t whole cube, the energy of interaction within zeta t whole cube will be equal to kBt, because that's the definition of a blob. It's the length scale where the interaction energy between two blobs comes the order of kBt. So, right? So this is by definition the amount of interaction energy in blob is equal to kBt, and then it will feel the presence of other monomers from a different blob. So that's why we have written kBt V GT squared by zeta t whole cube equal to kBt. That's the amount of interaction. Within a blob, you have approximate traction energy of kBt, right? So this cancels, and what you get is zeta t whole cube equal to v gt square, basically taking this side. And if we also use zeta t, the blob length scale equal to b into g to the power half, which is nothing but this relation, then from this relation we can once get rid of zeta t by substituting this quantity uh, here, right? And then what we have is gt depends upon b cube, which was the bond length, if you remember, b to the power 6 upon v square, excluded volume parameter, right? This is v square, and this is dimensions of volume. So basically this has dimensions of volume squared. This is again length to the power 6. So this is basically a dimensionless quantity which gives you number of monomers in a thermal blob, and this is defined by this quantity. On the other hand, in this equation, if you get rid of gt square from this equation again, then you can define the thermal blob length scale as b to the power 4 by v. So this has dimensions of L, and again you see that on the RHS of the equation has dimensions of L, and this is basically defines the size of a thermal blob in terms of microscopic quantities, but in terms of the potential, because the interaction potential decides the value of V, and the bond length is b to the power 4. Okay, so this is how the thermal blob is defined. So it is the length scale at which excluded volume interactions become important and become equal to kBt. So below this length scale, it is perfectly all right, valid to consider the conformation of the polymer chain to be ideal, which is Rg or whatever. Zeta g goes as zeta d goes as basically g t to the power half, ideal chain approximation, right? But above that, excluded volume interactions will become important, and you have to take t to the power 5 in terms of blobs. But let's cross check. So when v equal to b cube, okay, so in this expression, when v equal to b cube, which is the true also for a spherical thermal solvents, then you have a fully swollen chain. Okay, and then you see that the thermal blob size is equal to b. From this expression, thermal blob is the size of a monomer, right? So for a thermal solvents, the thermal blob size is that of a monomer. So it's always excluded volume interactions are important for a thermal solvents, because v equal to b cube. When v equal to minus b cube, which is basically a bad solvent, and you have a collapsed chain, right, then you get v equal to minus b cube. Again, the thermal blob size is that of a monomer. It's the size of the bond length or the monomer diameter, if you like, and it's a fully collapsed chain. So basically, never do you see a Gaussian, sorry, not a Gaussian, but n to the power half statistics. Rg goes as n to the power half statistics, because it is completely collapsed. Each space between this collapsed globule is full of monomers, right? And the thermal blob length scale is again equal to b. Now, what happens? So here, do you know the thermal blob is size of monomer? But if v decreases slowly, then you will see that zeta t increases. V decreases from this value, then zeta t increases. Then over a certain length scale, you do get to see ideal chain characteristics, even though you have excluded volume interaction and finite positive value of v. So I've just written zeta t equal to b to the power 4 by v, and so v is b to the power 4 zeta, so I've just rewritten it. Now the question is, for small chains, not relatively small chains, if zeta t is greater than the entire length of the chain, then though there is a finite positive value of v, you're going to always see the entire chain behaving like an ideal chain. Okay, so basically zeta t will be greater than the length of the chain. So when zeta t is greater than b into n to the power half, the total number of monomers in the chain, n is the total number of monomers in the chain, right? So if this quantity is smaller than b to the power 4 b into n to the power half, which is the entire chain behaves like an ideal chain, right? And if zeta t is bigger than this, b to the power n, so if zeta t is greater than b n to the power half, then this v, right, will be less than this quantity. B is this. This is greater than b n to the power half. Hence, v will be less than this quantity, right? So the thermal blob is larger than the chain size. So the entire chain behaves, for the entire chain, the ideal chain approximation is valid, right? So you can consider the entire chain to be ideal chain, whereas when v equal to b cube, then you have to always consider the entire polymer chain to be a Flory chain. It's a swelled chain. You have to consider at all length scales, right from the monomer length scale, individual monomer length scale, you have to consider it, the statistics is Flory like. But however, somewhere in between, so these are the two extremes, but when v is between these two ranges, then zeta t, then you have a length scale which is in between the monomer length scale. It's greater than the monomer length scale, but at the same time, it's smaller than the length scale of the entire chain. And then you have a length scale, zeta t. So polymers, the polymer segment below that length scale behave like an ideal chain, but larger than that length scale, you have to consider excluded volume interactions, right? So the point is that, see, if v equal to 0 again, the chain will always behave ideal, right? It will always behave ideal over all length scales. But we have a viable and a relevant blob or blob length scale if v is greater than v0, right? Uh, uh, so for when v is greater than v0, what is v0? It is this quantity, right? So v has to be greater than this quantity. Yes. So then we have a viable blob length scale, right? You will have a scale below which this polymer segment will behave like an ideal chain, and so basically from this, then we will have a valid definition of the blob only when v by v0 is greater than 1. Now v, I have just written, instead of substituted v0 as b to the power 4 b into the power half, that has to be greater than 1, and I come back to this ideal this chain interaction parameter. You remember this quantity? So you get essentially the chain interaction parameter n to the power half, the b cube must be greater than 1. And if this holds, then you have a valid blob length, or else the entire chain will behave like an ideal chain, right? So, so what is the point? The point is for a chain in good solvent or a poor solvent. In a good solvent, N has to be greater than zeta T. The total number of monomers basically will be greater than the blob length scale, right? And at this intermediate, and basically what you will have is swelling above this zeta T length scale, right? So at length scales, less than zeta T, it will behave like an ideal chain, or at polymer segment of length zeta T, it will behave like an ideal chain, but at length scales greater than that, it will behave like a n to the power 5. So the extent of the chain can be thought to be, first, blobs can't overlap because the interaction energy of overlap between blobs is order of kBt, or more is order of kBt. So blobs don't overlap. So the extent of the chain, the correct extent of the chain, can be defined as zeta T and the self-avoiding random walk of blobs. So n by gt power nu. This is the Flory exponent. Nu 3 by 5, right? And if you substitute these two quantities in terms of v and b cube, you basically get that okay, there's this prefactor, but r is still going as n to the power nu 3 by 5, right? So that remains, but over length scale smaller than the blob size, which is given this by this black circle, you have the ideal chain statistics, and only above that you have the self-avoiding random walk polymer chain statistics. If v is less than 0, not a perfectly bad solvent, but somewhere in the intermediate, then at this length scale, you have essentially again ideal chain statistics, but above this length scale, above these blue circles, these blobs represented by the blue circle, you have collapsed blobs. You can feel the interaction. At smaller length scales, monomers are unable to see the interaction. So the size of this globule, this collapsed globule of blobs, collapsed globule of blobs, because smaller than blob, it's still ideal chain statistics. So RGL equal to zeta T again, the size of a blob, because it's a collapsed chain of blobs, zeta T to n by gt, number of blobs to the power half. So this collapse is now in terms of blobs, and this is called a globule. Whereas, so that's in a poor solvent. Whereas in a good solvent, you will have R goes to the power n to the power nu, and that's called a coil. So as you change the solvent quality, the system will go from coil to globule to a perfectly bad solvent, where again the blob size will be the size of a monomer, which means the entire thing has collapsed. It's terribly bad solvent, and you won't see ideal statistics at ideal chain statistics at intermediate length scale. So that's the worst solvent, where the blob size is the size of a monomer. Everything has collapsed into as collapsed as possible. So basically what you could think is that thermal blobs in extremely poor solvent would attract not very poor, intermediately poor solvents attract each other like molecules in a liquid, and they basically collapse, and the shape of the globule is roughly spherical to minimize surface area of contact with the solvent, right? So you want to minimize the surface area of contact of blobs with solvent. So if you have a finite volume, to To minimize the area, it will take a spherical shape approximately. And what would be the volume fraction in a globule, collapsed globule? That will be NB cube. So basically, this is basically monomer fraction, monomer volume fraction, NB cube, number of monomers into B cube, divided by RGL cube, radius of globule cube. What was RGL? This was zeta T into N by GT to the power half. This was the number of blobs, not half, by 1/3. So you essentially have a melt of blobs. So it's a melt. Basically, all blobs are touching each other, and there's no space in between blobs. That's the melt of blobs. Whereas in a coil, you will have intermediate space, swelled. You have a chain of blobs which is swelled, and there will be space between the blobs. And hence you have R goes as at the power nu. Right? So if one has to have a phase diagram, not a phase diagram, I mean, if one wants to look at on a plot, on the y-axis, what you have plotted length, smallest length scale, B, length scale of a monomer, or the bond between adjacent monomers. And then as you go up on the log scale, you have zeta T, the thermal blob scale, and then R is the size of the entire polymer chain. And on the x-axis, you're going along the contour length, along the contour number of monomers, and the minimum number is 1. Right? This part actually doesn't make sense. The graph should start from 1. I mean, it is a mistake on my part to draw these lines from here. It should start from here, this 1, that's the smallest one monomer, and then you are going along the contour, increasing the number of monomers to GT, the number of monomers in a thermal blob, and then you go further in the log scale up till N. Right? So if you have an polymer in a thermal solvent, or in an athermal condition, then basically the monomer scale itself, the contour statistics, the conformation statistics will be n to the power 3/5. It should be, yeah, I mean, this is the statistics at all length scales. It should be more like g to the power 3/5, I think, because at all possible length scales. Whereas if you have a finite size of a thermal blob, then from 1 to GT, number of monomers, and this length scale, you will have an ideal chain. But above that, you can see the good solvent characteristics. So this is a self-avoiding walk of blobs. That will go as number of blobs to the power 3/5. So n to the power 3/5 will be the behavior. If you have the theta solvent, it will remain ideal at all length scales, right? And also, if n was smaller than GT, then you will always at all length scales along the polymer chain, again you will see ideal chain statistics. But if n is greater than GT, then you will see n to the power half if it's a theta solvent. But if it's a poor solvent, then up to a certain length scale you will see ideal chain statistics. But after that, you will have a collapsed globule of blobs n to the power 1/3. And on the other hand, you have extremely non-solvent. Then right from the monomer length scale, you will see the polymer conformation to be n to the power 1/3, the same one, right? At all monomer length scales. So this figure is given in page 114 of Rubinstein. And the last thing I want to mention in this part is, in the Flory theory, we get nu equal to 3/5, which is equal to 0.6. But there are various more accurate theories where nu can be calculated as 0.588. I mean, 588 over 0.59. But it's a very small difference, as you see, 0.6 and 0.588. So at times, for the various exponents, that we calculate, people use this formula, especially Rubinstein at times uses this formula, but we will stick to 0.6 or 3/5, okay, when we convert exponents in future, such as here and so on and so forth. So we'll continue in the next module. Okay, so stop sharing and stop recording.